Okay, so welcome. We're going to do gyroscopes today. Okay, so what we're going to do is we'll do a bit of our derivations to start with so that we've done the maths part, and then after that we're going to watch some videos which demonstrate how the gyroscope works. Okay, so from lecture 14, the angular momentum of a spinning rotor so we can do it in two forms. We can do it the scalar form. We can just write that h is equal to I omega, so that's the scalar version, or as a vector, the vector h is equal to I times the vector omega. Okay, so they're the So somebody asked a good question, because I've mentioned doing this before. So what's the difference between the two? Well, if you have a vector, okay, if the dimension of the vector becomes 1 by 1, then it's a scalar, isn't it? Okay, so if you're trying to do something in more than one dimension, okay, then it has to be a vector, okay, because you have more than one coordinate. Okay, but if you shrink the vector down to a 1 by 1, then it becomes the scalar version. Okay, and we'll switch between these depending on when whether it's appropriate. So we also did in lecture 14 about the moment. Okay, so the moment, or sometimes people refer to torque, is equal to the rate of change of h So if you remember back to lecture 14, we did h dot, didn't we, which is d by dt of h. And we had some relationship that the moment is equal to dh by dt. And of course, because h is also I omega, this is also d by dt of I omega. So here I'm just using scalar variables here, okay, just to keep the notation simple. And so we can rearrange that, so we have d I omega equals m times dt. So I'm going to try and draw a diagram now to explain how the gyroscopic moment is derived. Okay, so the thing we're going to look at in gyroscopes is the creation of this moment effect. Okay, so let's draw a diagram to try and represent that. And it's going to be our normal ijk axes. But as we did last lecture, we're going to draw them in 3 dimensions now. Okay, so we're going to have them like this. And we're going to have I, which is, of course, is the x direction. Along here, we're going to have j upwards, and that's, of course, the y direction. And we're going to have k along here, and that's the z direction, isn't it? Now, as we've always done, we've always had omega acting around the k-axis, haven't we? Okay, so this is the angular velocity. Okay, and we'll continue to do that. And in a minute, when you see the gyroscopes, this k-axis is going to be the spin axis. Okay, so what we'll do to create a gyroscope is we get a circular disc, and we rotate it round at high speed, and it's going to be rotating around this axis, the k-axis. Okay, so that's the spin axis with omega. Now, we've got these other 2 axes to think about, and this vertical one here is going to move with an angle we're going to call capital omega. Okay, so this is the capital omega. Okay, Now this j-axis is we're going to call the precession axis. Okay, and if we take omega to be equal to psi dot, okay, so psi is an angle, and so d psi by dt is the rate of change of the angle, or the angular velocity in this along this axis. Okay, psi is the precession angle. And so this final axis, the I-axis, we're going to call the moment axis. Okay, and so that will have a moment acting around it, and we're going to call that capital M. Okay, so in our 3D space, we've got three axes, and they've each got something acting around them. One is the spin, or the rotation of the gyroscope, one is the precession, and one is the moment. Okay? So in terms of our I omega, let's just have a think about what's happening. Well, if we draw a small movement in the precession axis, so if we have, so this is in the plane of k and I now, okay? So previously we haven't considered applications where we're in the plane of ki, have we? We've always been in the plane of ij, okay? But now for this application we're going to consider some movement in the plane. That's why we've introduced this new angle psi, okay, which represents these sort of movements. And here we're going to have a small movement. So this is going to be d psi, okay, to represent a small angle. Okay, now what's happening around this axis is rotating with omega, and so the I omega effect is going to be in this axis. Okay, so this length along here corresponds to I omega, and this part here corresponds to di omega. And the reason that derivative is here, if you remember when we did our derivative of vectors, you always end up with an angle change of 90 degrees when you take the derivative of a vector. Just like in the complex plane, if we had imagine we were thinking about our exponential solution that we had e to the I omega t, didn't we? And if we take the derivative of it, we get I omega t coming down as a factor in front of the e to the I omega t, so that's like a rotation in the complex plane of 90 degrees. Okay, so we have this kind of relationship in this space. Okay, and so from that 3D space we can say that the tan of d psi is equal to di omega over I omega, and we've defined d psi to be small. So as is small, the tangent of the small angle is just equal to the angle, approximately equal, we'll say, so they are approximate equal signs. So that gives us the relationship that di omega is equal to d psi I omega and if we divide both sides by dt, we get d by dt I omega is equal to d psi by dt I omega. Well, this left-hand side is equal to the moment, so this is the derivative of the thing we started with, which is the angular momentum. So we end up with m is equal to d psi by dt, that's the precession, okay, the rate of precession, large omega. And then we have I omega. Well, I is the moment of inertia. That's a scalar constant. So I'll bring that to the left-hand side, and then we're left with the spin rate of the spin axis, small omega. Okay, so in vector notation, it won't take you much to work out that m, the vector, is equal to the moment of inertia multiplied by the precession rate vector, cross product with the spin rate vector, okay? Now one subtlety, so I've kind of gone through this derivation using scalars, okay? So one thing to just watch out for is here, you'd be, in a scalar case, you could multiply these together either way around, it wouldn't make any difference, okay? But in the vector case, if you change the order of multiplying the cross product, you change the sign of the result, don't you? Okay, so it always needs to be in this order. And so these equations, this is what you need to solve gyroscope problems. And what it says, if you think about what it's saying that the gyroscopic moment, m, is equal to the moment of inertia multiplied by the cross product of the precession rate with the spin rate. Okay? So in a minute we're going to look at some videos, but one way you can think about this is about riding a bicycle, okay? Because so most of you ride a bike, okay? So if you think about, you're sitting on your bike and you're riding along, the wheel is spinning, okay, so that's the spinning disc. Okay, so like the k-axis is going through the axle of the wheel. Okay, now if you want to turn, what you don't, like, well, it's complicated, okay, but if you want to turn, you don't have to have your hands on the steering, like, on the handlebars to actually turn, do you, right? You can ride you can ride with no hands, and you can still turn your bike. Okay, so what you do to turn your bike without any hands is you just shift your center of gravity. So what you do is you apply a moment. Okay, so as you're riding along, you lean slightly, right, which is applying a moment along the moment axis, and what happens is your bike then precesses. Okay, so your bike actually starts to turn. If you're leaning right, it turns right, and so on. Okay, so we'll see some more in-depth examples in a minute, but that's just one very simple way of trying to think about it. And if you're stuck trying to think about the axes, all right, usually the bicycle is the most like relevant one that people can work out from what's actually going on. So let's just think about this cross product again, okay, because this will come up time and again. So if we think about the vector form, the angular velocity of the spin rate is equal to the scalar spin rate times k, isn't it, using our notation? But now we also have things happening on the other two axes. Okay, so we have a vector of the precession rate, okay, so that's equal to the scalar times j, and then we have the moment, okay, which is equal to the scalar value of the moment times I. Okay, so if you think about trying to solve this gyroscopic problem, these things are all connected to each other. Okay, so if you change one, it has an effect on the others. Okay, so let's just think about how what that means. Okay, so if we draw a little sketch. Okay, so this is the one we normally draw. I and j, k is out of the page. Okay, and small omega acts like this, doesn't it? Okay? And that's the positive direction. Okay, so if we're trying to solve these problems, we're trying to work out which is the positive or negative direction of the angles. So in the other planes, we have this, we have the precession rate, large omega, positive like this, and we have the moment acting like this. Okay, so sometimes what you have to do is, if you look at a question in a tutorial sheet or an exam, very often it's relevant. It's telling you something relevant to the object. So, for example, an aircraft with a spinning propeller, okay, is one example of something that comes up in exams, or a gas turbine engine with a spinning shaft. Okay, so you have to think, okay, what's the spin axis? What's the precession axis and what's the moment axis, okay? And then you draw those. Once you've defined what those are, then you can think about in each of the planes, which is the positive direction of of these three quantities, okay? And then you can kind of work out from the question that you're being asked whether you're being told that something's in the positive or in the negative direction, okay? Once you've got that information, you can plug it into either of these equations, okay, and do the cross product or do the scalar product if it's a scalar case, and then you can come up with an answer. So let's just think about this cross product for a moment. So m is equal to a scalar value I times this cross product. So what does this cross product look like? Well, it should look like this. So we'll have, okay, because this is a scalar value large omega times j, there's nothing on the I and k parts of this vector, okay, so it's just got a j component. Similarly for the small omega vector, it's just got a k component, okay, so there's 0, 0, k. So if we do the cross product of these two vectors, what we get is the scalar quantities, large omega, small omega, multiplied by I. Okay, yeah. Sorry, yeah. I've written K again, haven't I? That's what happens when you get old. You guys are lucky when you're young. Make the most of it. Brain starts to deteriorate after a certain time. So, anyway, small omega, you're absolutely right. So what this is saying to us is that if we do a cross product, okay, we've got precession rate in the j-axis, we've got spin in the k-axis, but the cross product gives us something in the I-axis, okay, which is exactly what the moment is defined as, isn't it? Okay, so the moment is defined as some scalar quantity multiplied by the I-axis to tell us it's a rotation around I, okay? So this is equal to m the vector, and of course we know that m the vector is a scalar m times I, so that m the scalar is just equal to, well, it's the moment of inertia, isn't it? So this needs to be times by, if we times that by I, we get that, don't we? Okay, so we can recover our scalar version from this cross product. So just to note what I said, switching the order, so small omega crossed with big omega gives minus m, okay, because you end up with the cross product. By definition, if you switch the order, it gives you the opposite sign, okay, and that's because you end up with k times j, which is minus I, instead of j times k, which is plus I, okay? So just be aware of that. And just to reinforce, because some people in tutorials have been asking these kind of questions, if you get really stuck, okay, you can always just do this. Okay, so you can always just write down what I, J, and K are, if you're not sure. Okay, so you can always write these down, and then you can work out what they are in the cross product. Okay, by doing this kind of calculation. Okay, so if you can remember how to do cross product, you can always just think, okay, I'm stuck, I'm in an exam, I don't know what this is, but if I just work this out for myself, I can find out whether it's positive I or minus I or whatever. Okay, so you can always just go back to these vectors if you want to. So we're going to watch some videos now, and hopefully the sound will work as well. Okay, so we've got a few videos to watch. Some of you might have seen this before for the basic toy gyroscope. Okay, so the first one is about a toy gyroscope, which basically shows you some of the things that it can do. Then there's a video with a slightly crazy Frenchman, which I like, describing how gyroscopes can be used to do attitude maneuvers for satellites. Okay, and then the third thing I want to show you by video is it's a description of archive footage of original rockets. Okay, and how gyroscopes were used in rockets for guidance and control. Okay, and they still are now, but they've obviously, well, there's two things: they've evolved a lot, and secondly, people aren't allowed to give lectures about what's in rockets that are made today. Okay, so what we do is we give you some information about the sort of historical context. Okay, because I wouldn't be allowed to tell you what was in a current rocket. That wouldn't be good. Right, so the first thing is the toy gyroscope.
It consists of a metal wheel mounted on an axle. The wheel and axle spin freely, secured in a metal frame. This simple device can behave in the most unexpected ways. The components of this simple mechanism are obvious, and it doesn't seem to have any special capabilities. Try to stand it on end and it falls over. Try to suspend it like this and it drops. Apparently it can't defy gravity. But spin the wheel and all that changes. A string provides a simple method to spin the wheel. First thing I notice about the spinning gyroscope is that it resists attempts to change its position. A resistive force appears when I attempt to tilt or rotate the gyro. Now when I stand it on the tabletop, it stays vertical. The spinning wheel is creating a force that holds the gyroscope upright.
You should have said moment. It's creating a moment.
The wheel stops, the force disappears, and the gyroscope falls. Incredibly, this force will support the gyroscope like this. It appears to be levitating.
So why is that happening? Does anyone know this? Seen this before? Seen that before? It's like magic, right? You know, it's not really physics, is it? It's just like suspended in it. What's happening is it's precessing. It's spinning and precessing. If it wasn't precessing, it would just fall over. Okay, so if you watch it again, it has to precess to create the moment, which is the moment is actually pushing the free end up. Okay, so the precession rate is going around fast enough to make sure that spin rate times precession rate is big enough moment. That's why it's actually going around quite quickly. So if you look, right, it has to precess quite quickly to get enough moment to stay from falling down.
The gyroscope will balance on a string. You can even lift the gyroscope with a string looped around one end.
So again, it has to process to do that, right, to create the moment.
This interesting behaviors.
So that's the basics of how a gyroscope works. Okay. Now they're used extensively in aerospace engineering. If you put the gyroscope inside a gimbal, okay, a gimbal is like a frame that holds it. What happens is, and you attach the gimbal to the aircraft, as the aircraft and the gimbal move, the gyroscope tries to stay in the same place, okay? And so they were used a lot for sort of giving pilots horizon coordinates, okay? So wherever the aircraft was moving, the gyroscope would stay essentially on a sort of horizontal horizon if you set it up that way. And so that's a traditional way that they've been used in aerospace engineering. Another way they've been used is in satellite and spacecraft. And this next video is a bit mad, but I quite like it because it describes it quite well. It shows you how you can use a gyroscope to control something in space where you can't generate a reaction force, okay? So you can't have a reaction force in a spacecraft because it's in free space, it's moving around. So to create a force to actually move it, to change its attitude facing towards the Earth, okay, you need something like a gyroscope. You could do it with rocket fuel, right? You could have a rocket, but that's really expensive. Okay, so a gyroscope is cheap, and once it's there, all you have to do is find a way of spinning it, okay, and then it creates a force for you. Okay, so that's why it's like used in space applications.
What are you doing? Oh yeah, I am preparing my course on spacecraft attitude control using control moment 0. I will explain to you. Think that this rotating armchair is the Earth observation satellite. The Earth is represented by the map on the wall, and the payload of the satellite is the laser beam. Okay. And we want to control the position of the laser beam on the Earth. So to do this, it is very easy if you can put your foot on the ground. But in space you are not allowed to take support on the Earth. And so it is not very easy to apply the torque and to control the position along the vertical axis. Here only we are considering the vertical axis. But it is possible if you use gyroscopic effect. And for this, you have to spin the wheel like this. So this is the direction of the angular momentum, and we are going to apply the velocity on the precession axis to have a torque along the third axis. And you can see that now it is possible to control the position of the satellite without putting the foot on the ground. And we can apply some torque on the satellite. Okay.
So this person's mad, aren't they? Right? He's basically cut the front off his bicycle and welded it to his office chair, right? To demonstrate to you how to change the direction of a satellite. Okay, so but I like it. I like him. So just think, what did he say? He said the spin axis, right? So he didn't call them I, J, and K, but for us, so this is the spin axis. It's K, isn't it? So the wheel is spinning around the K-axis, okay? And then he said the precession axis, okay, which is the J-axis for us, okay? And then the final one is the moment axis, okay? So if you look, so now look, the moment axis is basically the vertical axis through the bottom of the chair, isn't it? Okay? So what he does is he spins the wheel, and now he's got a control like this lever which can move the precession backwards and forwards. Okay, so because he can pull the precession backwards and forwards, what he does is he then generates a moment around the I-axis, which is the vertical one on the chair, right? So the example I gave to you about the bike is you're changing stuff around the moment axis and you're getting a precession. Okay, so the spin stays constant, and then you either change precession to get a moment, or you change moment to get a precession. Okay, so that's the way that you can use the gyro to your advantage. I stopped him. Sorry, I stopped him. Let's listen to the end of what he has to say, because there he is. And so his laser pointer and the map stuck on the wall, that's supposed to be the Earth, right? And he's in the satellite, and the laser pointer is, where we're pointing to on the Earth. He's an unsung hero. Okay, so this last video is a little bit longer, and it talks about how gyros are used in the control of rockets, okay, and it shows some archive footage about the V2 and the rocket, and what was happening at the time in terms of developing rocket technology, okay, and gyros were a big part of that.
Just take a look at this V2 archive footage. The V2 is shown hanging in the air over the firing point, probably because the turbo pump is under running. So instead of the motor delivering 25 tons of thrust, it's probably only delivering somewhere between 12 and 13 tons. And the only reason the rocket is climbing at all is because of its use of propellant. But you'll notice that something is keeping the rocket upright as I was trying to keep my broom here.
These gyroscopes are the brains of the rocket. They are in universal mountings. Electrical pickups measure the movements of the gyroscope and translate these movements to the carbon vanes and the trimmers in the tail unit. These vanes and trimmers direct the rocket both in bearing and elevation along its trajectory and prevent any deviation from its planned course. The 4 vanes are in the jet of the rocket, and there is a trimmer on each of the 4 fins. This knock-up represents the inside of the control compartment in the rocket. In the background is a skeleton tail unit, with the vanes and trimmers in position. As the control compartment moves, the gyroscopes move in their mountings, and these movements are conveyed through electric cables in the rocket to corresponding servo motors in the tail unit. There is a servo motor for each carbon vane and trimmer. The servo motors move the vanes and the trimmers to counteract the original movement of the control compartment and to keep the rocket on its course. This gyroscope controls the elevation of the rocket by moving a pair of the carbon vanes, thus turning the rocket from the vertical over to an angle of 43 degrees. The other gyroscope controls the direction of the rocket by the movement of this pair of vanes.
Let's take a closer look then at a real gyro platform from a rocket. Here's one from the German V2 ballistic missile. It's fairly well laid out here. One of the great things about looking at the V2 is we get this very basic, very simple design of the gyro platform. It really lets us see what's going on. We've got two gyroscopes side by side here with their axes at 90 degrees to one another. We can see the gimbal mount here that the gyroscope rotor is in. You see the gyroscope rotor with its casing there. Other little detail to pick up is this little stud in the centre. It's a little platform with a little stud on it. If we look over at this one over here, we can see a lead weight has been attached to that. Almost certainly, as part of the assembly process, actually getting the gyroscope in trim and in perfect balance. We can also see there's a little stud there and another one over here. Almost certainly used for adding tiny weights to that to actually get it into balance. Another little detail I want you to notice is this assembly on the end of the gimbal here. This is actually a potentiometer. It's like a volume control of a radio, and this is actually used to determine the position of the gimbal when it's in motion. So, let's try to get an understanding of the properties of the gyro that can be harnessed to actually control and guide the rocket. To do that, we're actually going to look at a rather popular toy.
So we're not going to look at the toy again.
Gyroscope is still a popular toy, maybe.
But I just want to show you at the end, he shows how it works in a gimbal, which is useful. So he's putting the gyroscope inside a gimbal now, which is what I mentioned before.
Yeah, wonderful piece of engineering. Not really going to win prizes, I don't think. But I think it'll do for our coach. I'm just going to squeeze that together. Okay, you can see I may have to make some little. Actually, it's not that bad.
So it gives like full 3D motion. So you've got two gimbals, one in each direction, attached to like a frame.
Here, the gyro is now free to move at any angle. And this is going to give us a much better chance to show you one of the principles of the gyro that really weren't shown by those other demonstrations, and it's the key one that's actually used for guiding a rocket that's trajectory of travel. Got plenty of rotation on there. There it is, operating. Now watch what happens as I move it around. Can you see that the gyro is actually retaining its position in space? It'll start to be overcome by the friction of the bearings as I move it around. It won't be quite so happy, and it will start to creep off and it will start to precess. But you should be able to see there that the gyro is actually fighting this. And we can sort of, there you go, it's gone into gimbal lock there. Did it again. Okay. Now, using that principle of the gyro holding itself back, you get a very interesting effect if we try to actually tap this backwards and forward. You can see there's a very peculiar kind of motion being induced in the gyro as I try to do that, as I try to turn it around. Now, using this ability of the gyro to resist movement of its position, all we've got to do is introduce some method of measuring the change of angle between the gimbal frame here and the architecture of the metalwork that's actually holding it. Let's call that the rocket body itself. Now I'm going to do that.
So I don't think we need to go through his little cardboard angle thing. I think we've got enough of an idea. But essentially that sort of gimbal frame is very crudely shown there, is what you have either in rocket, satellite control, or even aircraft guidance systems as well. Okay, so they're all based on this concept that the gyro, when it's spinning, will essentially try and maintain a constant position, and so the gimbal frame allows sort of the, whatever it is, the aircraft or spacecraft, that 3D movement in space. Okay, so that's it for today. I'll see you all again on Friday for our tutorial.